Hello guys, welcome to my YouTube channel. In this video, I am going to teach you the remaining parts of surface chemistry. If you didn't see that beginning parts, just go and watch my previous videos and come back. This is the continuation of those videos. Okay guys, please subscribe my channel if you didn't subscribe it, and comment me for any videos you want. Okay guys, let's move on to the chapter surface chemistry. Just we will see a little bit recap about the chapter what we had been seen. Adsorption, we had been seen about adsorption. In adsorption, absorbent and absorbate and absorbate and absorption. In absorption also we had been seen types of adsorption. We had been seen physical adsorption and chemical adsorption, difference between physical and chemical adsorption, factors influencing adsorption, and somewhat adsorption of gas in solids, and adsorption of solids from solutes had been seen. Types of adsorption, positive adsorption, negative adsorption, and their example factors influencing adsorption of solution from solutes from solution. Adsorption isotherm, 5 different types of adsorption isotherms. Now we are going to see about Fedling's adsorption isotherm. What is meant by Fedling's adsorption isotherm? The relationship between the magnitude of the adsorption x by m and pressure P can be expressed in the terms expressed mathematically by an empirical equation known as Fedling's adsorption isotherm. Here itself they had been given, it's an empirical equation and expressed mathematically. They are explaining mathematically, it is not theory based, it is mathematically based expression. Okay, x by m. I have been said what is meant by x and m in my previous videos. Just you can see that for your clarification and all. Okay guys, just once again I will say x is the mass of the absorbate and m is the mass of the absorbent. X is the mass of the absorbate and m is the mass of the absorbent, and capital P is the pressure. The example x by m is equal to kp 1 by n as equation of Fedling's adsorption isotherm. Next, move ahead. I will say the difference. Let's see the differences afterwards. Then it will be clear for us to see that. Okay. First, you will see the definition of adsorption and derivation of Fedling's adsorption isotherm. The equation of Fedling's adsorption isotherm may be derived from the resultant of observing from the graph. By observing the graph itself, you can able to write there what will happen at low pressure, what will happen at a high pressure, and at intermediate normal pressure also. First of all, you can just take few minutes or seconds to see the graph, what is given in the x-axis, what is given in the y-axis, how the slope is going on, how is the line, what is intercept is equal to log k. You can able to see that in y-axis we had been given log x by m, and in the x-axis we had been given log p. It means by pressure. At low pressure you can able to see adsorption increases with pressure. If there is a low pressure, surely it will be increased. By that we had been seen in our previous video, the adsorption increases with the pressure. That only they had been given here. It's given as x by m is directly proportional to pressure. You can able to see there is an increase in the line slope with the increase in pressure. At a point it becomes constant. It is not a matter. First from the beginning it's increasing, gets increased. So it is replaced by a constant, directly proportional, replaced by a constant. X by m is equal to kp. A constant is introduced in that place. At a high pressure, what will happen? Adsorption almost constant. At a high pressure, you can able to see that the graph, it has been reached the equilibrium. It is known as the dynamic equilibrium. At that place, the absorption will be directly proportional to the disabsorption. So it is given as a constant. X by m is equal to a constant, or x by m is a k is the constant. We are using k as a constant. In these terms, at intermediate normal pressure, adsorption depends upon on 0 to 1 power. It's an intermediate thing. Can know of pressure. Fraction rises up to the power of pressure. We are giving the fraction in this place. We are introducing fraction in this place because it is an intermediate. Example, they had been given in the bracket itself. Fraction raised to the power of pressure. They had been given x by m is directly proportional to p, and the fraction is 1 by n the power. and also, or you can also write as x by m is equal to kp 1 by n. N is a whole number and 1 by n is a fraction. You know that the equation 1 is called as Fedling's adsorption isotherm. The equation 1 is known as Fedling adsorption isotherm. We also take log on both sides. The above equation can be written as, the first equation can be written as by taking log on both sides. By log on both sides, the above equation can be written as log x by m. You know how to take log. The above power will come in front like this. Log x by m is equal to log k plus 1 by n log p. On plotting the log x by m versus log p, a straight line is obtained with a slope of 1 by n, the intercept of log k. You can see this graph had been given clearly in this graph. What will happen on all. Okay guys, next we will go to the disadvantages or limitations of Fedling's adsorption isotherm. Well, disadvantage Fedling adsorption equation is purely empirical and has no theoretical basis. I have been said before itself, it does not have theoretical basis. It only have it is purely empirical. Fedling's equation is purely empirical and have no theoretical basis. The equation, second point, the equation is valid upon only up to a certain pressure and invalid at high pressure. You can able to see that at a high pressure they reaches a dynamic equilibrium. So it is valid only at certain pressure and does not it is not valid at high pressure, invalid at high pressure. The constant k and n, we had been introduced the constant k and n in the fraction 1 by n. N is a whole number. We had been said that it is not constant. The constant k and n are not temperature independent. They vary with them. They are not temperature independent, but they also vary with variation in temperature. And fourth point, Fedling's adsorption isotherms falls when the concentration of the absorbate is very high. Fails. Fedling's adsorption isotherm fails when the concentration of the absorbate is very high. Okay guys, this is we had been seen about Fedling's adsorption isotherm. Now we are going to see about Lagrange's adsorption isotherm. I will say the differences between Fedling's and Lagrange's. It will be if you know the differences, you will be clear with that, so you can able to understand easily between them. You will not get confused. As first we will see about Lagrange's and then we will go about the difference between them. Okay, Lagrange's adsorption isotherm. Lagrange's adsorption isotherm. Lagrange derived an equation based on some theoretical conditions. Lagrange is a theoretical condition based equations. The postulates or assumption of Lagrange's theoretical basis are the assumptions. I will show you a picture and explain with the picture. This will be helpful for you to remember very easily. Just see the picture and observe it. I will say each and every point and explain it. It will be very useful for you. Valencies at the surface of the absorbent are not fully filled. Valencies, you can able to see there is a valencies or gap between two molecules. So the valencies at the surface of the absorbent are not fully filled. You can able to see that. It's a first point. With this picture you can able to write the postulates of Lagrange's or assumptions of Lagrange's. The absorbed gas layer on the surface of the absorbent is 1 molecular thick. The absorbed gas layer on the surface, solid surface, is only 1 molecule thick. The surface of the solid is homogeneous, so the absorbed layer is uniform all over the absorbent. You can able to see not the light colors, the dark colored circles with you can be able to see that the bigger circle just 1 inch bigger than the smaller circles. You can able to see that it is arranged uniformly throughout the solid surface because it's an homogeneous. The solid is homogeneous. This is the third point. And the fourth point is there is no interaction between the adjacent absorbed molecules. You can able to see there is no interaction between the adjacent absorbed molecules. If there is an interaction, they will move here and there, or they will attract each other, or they will repel each other. Anything will happen. There is no interaction between the adjacent absorbed molecules. So only there is a valency or at the surface of the absorbent. These 2 points or vice versa. You can able to memorize understand with the help of this also. The absorbed fifth point, the absorbed gas molecules do not move around on the surface. You can able to see that the absorbed gas molecules, the bigger circles with the dark colors, they are just in the uniform as a layer. They did not move around move around on the surface of the solid, means absorbent. So only they given the fifth point as absorbed gas molecules do not move around on the surface. Okay guys, I will show the points also. These are the points. If you want, you can just note these points, make the note, it will be helpful for you. Next we had been going to see the derivation of the Lagrange's isotherm. According to Lagrange's assumption, when the gas molecule strikes a solid surface, some of the molecules are absorbed and some of them are disobsorbed. Thereby the dynamic equilibrium is established between the absorption and disadsorption. If A is gas molecules and M in the surface, then you know that only the molecules which the solid needs, they will absorb that, and other molecules are repelled. It's known as absorbent and repelled. Okay. Thereby the dynamic equilibrium is established between the absorbed and disobsorbed molecules. If A is a gas molecule, you can see the equation AM. G is a gas. A is a gas. You can there. So only they had been given G there. Plus M is a surface. Just we had using the constants A and M, surface. Thereby KD. You can able to see there KA and KD. Okay guys, KA and KD is there. KA is an adsorption constant, KD is an disadsorption constant. Thereby the dynamic equilibrium is established and thereby they are given as AM. Let fraction of you can see, let the fraction of total surface area covered by the absorbed molecule, the total surface area covered by the absorbed molecules are considered as the theta, and the fraction of the uncovered area, you can see the fraction of uncovered area. Just a minute, this picture will be very much clear for you. This picture guys, this picture will be very much clear for you. With this you can able to see the fractions of total surface covered by absorbed molecule is theta, and the fraction of uncovered area is 1 minus theta uncovered area. You can see that, and the rate of disadsorption is proportional to the rate of adsorption. Wait a minute guys, I will show you. Okay, you can able to see that the rate of disadsorption is directly proportional to the number of absorbed molecules RD and KD by theta. KD is the rate of disadsorption. I have been said in that equation itself. Thus the rate of adsorption is directly proportional to the uncovered area. Adsorption depends upon the area which they give. If everything is covered, the absorbed molecules cannot go inside the absorbent. So the rate of adsorption is directly proportional to the area available uncovered area, or A is equal to Ka 1 minus theta P. Ka is the rate constant for absorption. Okay guys, then you can able to see here equilibrium between at equilibrium. This is the equation. The rate of disadsorption here itself you had seen the rate of disadsorption is directly proportional to the rates of adsorption. So we are giving that KD is equal, KD theta is equal to Ka 1 minus theta P. We are substituting that values here there, and just we are multiplying Ka and Kp into the brackets 1 and minus theta. We are getting an equation Kd theta plus Ka theta P. We are bringing the theta values to the left hand side and the values without theta on the right hand side, and then we are taking the theta as a common. By that we are getting theta Kd plus Kap is equal to Kap, and bringing that to the denominator, we are getting the value of theta Kap divided by Kd plus Kap is the first equation. You can keep it that first equation, and by dividing the equation with the Kd, we are getting Kd by dividing theta is equal to Kp 1 plus Kp. You can ask what is the capital K. Capital K is an equilibrium constant, also known as adsorption coefficient. By replacing that, we are getting this. Next we are going to move to the next thing. By moving to the next thing, but the amount of gas absorbed per gram absorbed, x is proportional to theta. Here itself you can see we had been introducing theta. Fraction of the total surface area covered by the absorbed molecules is known as theta. We had been find the theta value by substituting the theta value there, and to remove the directly proportional symbol, we are using equal symbol by introducing a constant k dash. It is a new constant, guys. The equation 4, the relation between the amount of gas absorbed or to the pressure. The relation between the amount of gas absorbed to the pressures at pressure of the gas at a constant temperature is known as Lagrange's adsorption isotherm. The above equation 4 may be written as 1 plus we are alternating the same equation into different equation to get the p by x value. So with the help of that we can able to plot the graph, so only we are doing that. After that the equation is similar to the straight lines equation in max. You had been studied y is equal to c plus mx equation. It has been given that we are having that equation. With the help of the equation case 1, just we go to the case 1. At low pressure, if the pressure of P is very low, then the value of k by k dash by k p term will be neglected because it is very low. So we are not using the term in that place. We are getting the graph for the slope like this. With the help of that, we are getting an equation as k is directly proportional to pressure at low pressure. At high pressure, you can able to see that 1 by k dash and k is neglected. It's a less value, so we are neglecting that. By that we are getting is k is x is equal to k dash and p not power. Okay, we are going to move to that. The third case, external adsorption is depends of pressure. Extent of adsorption is depends of pressure, depends independent of pressure. Sorry guys, extent absorption is independent of pressure of the gas because of the surface becomes completely covered at the high pressure. We had been talked about that before before previous slides itself. At normal pressure, in third case, at normal pressure, the power between 0 to 1, you know that. At intermediate also, x is equal to k dash, p not we had been used, here we have been used pn. Eighth equation, this equation is known as Fedling's adsorption isotherm. In Fedling's itself, you had been seen that. Okay guys, in this, what is the merits and demerits, limitations? Lagrange's adsorption isotherm holds good at low pressure but fails at high pressure. Same thing here also guys, at high pressure this will fail. According to Lagrange's adsorption theory, the adsorbed is mono-layer, but multi-layer adsorption is also possible. Mono-layer adsorption we had been said here, but multi-layer adsorption is also possible. In previous video I had been said about that. Previous videos I had been said about that. Multi-layer adsorption is also possible. Okay guys, contact theory or role of adsorbent we will see in our another video. Just I want to say something more to you. Just fundamental difference between the Lagrange's and Fedling's. With this you can able to remember easily. Fedling's adsorption isotherm, Lagrange's model was a theoretical constant, while Fedling's adsorption is an empirical. I have been said this. In the Lagrange's model, it is assumed that at maximum covered there is only a monomolecular layer on the surface. Lagrange's, that means there is no stacking of the absorbed molecules. The Fedling isotherm does not have a restriction. In Lagrange's you can see there is only monomolecular thick, but in Fedling there is no restriction. You can see the graphs also guys. Okay guys, thank you for watching my video. If you have any queries, just comment in the comment box. Thank you for watching guys.